In the previous video, we have defined the resultant of two polynomials as the determinant of their Sylvester matrix. Furthermore, we have shown that the resultant could be used to check whether or not two polynomials have a common zero. We actually use this problem as the motivation for the definition of the resultant. Alright, so that's one application of the resultant. Is that all it's good for? Well, only if we have a limited imagination. If we think more flexibly, then we can find many interesting usage for the resultant. In this video, we're gonna give an example of a usage of resultant in elimination theory. We can see how the resultant can be used to eliminate variables and thus to find implicit equation for parametrized variety, for example. Suppose we are given the following parametric plane curve. How would we find an implicit equation for this, i.e. an equation involving only x and y without the parameter t? Equivalently, how do we eliminate t from this system of equation? Later we'll see that we can also do this using Grosvenor basis. But for now, let's try to find this equation using only resultant. Well, so far, besides the definition, we have only one alternative way to think about the resultant. We can think about it as a way of detecting whether or not two polynomials have a common root. So we need to rephrase this problem as a problem about common roots of some polynomials. And here's where we need to get a bit more creative. Let us call this parametric curve C. Then saying that C has this parametrization is equivalent to saying that a given point x0, y0 lie in C if and only if there exists some time t0 such that the following equations hold. That is, if and only if the following polynomials have a common root, t0. So we got the magic word, common root. This is just equivalent to saying that the resultant of these two polynomials, right, with respect to t, viewed as polynomial in t, is 0. Thus we can think of the curve C at the set of points x, y, for which there exists a t0, such that these equations have a common root, i.e. the set of x, y, such that the resultant of this polynomial here, with respect to t, is 0. So now here's the change of perspective. We can just view these as polynomials in t with coefficients in kxy. In which case the resultant here is gonna be a polynomial in kxy. Observe that the resultant is always gonna be in the ground field, and here we're assuming the ground field is kxy. This, by the way, is the reason why we need to specify a variable when taking the resultant. Because in a polynomials there might be many choices for what should be viewed as the variable and what should be viewed as the coefficient. Okay, so if we view these polynomials as having coefficient in kxy, then the resultant is going to be a polynomial in xy. How does that have anything to do with our original problem? Well, this polynomial is the implicit polynomial for x and y. Because observe that a point x, y lie on the curve C if and only if it satisfies this polynomial. So the moral here is that every time we take a resultant with respect to a variable, we eliminate that variable. When we have three variables x, y, t, and we eliminate t, what we get is a relationship between x and y, and thus an implicit equation for a curve. Of course, this also works for higher dimensional variety. There's no reason to stop at curve. But for more complicated situation, it might be easier to use Grosvenor basis. Now before we end, let me just show you the explicit equation, just to review how to compute resultant. Remember, to form the Sylvester matrix, we want to write down the coefficient of the first polynomial. And on how many rows do we write it? Well, as many rows as the degree of the second polynomial, so for 3 rows. And similarly, we continue writing the coefficients of the second polynomial as many rows as the degree of the first polynomial, so for 2 rows. And if we take this determinant, we'll get this polynomial, which gives an implicit equation of the curve C. In the next video, we're going to talk about another important application of resultant, namely to count and find intersection. Then we'll use it to give an elementary proof of Bézout's theorem.